In this video, I'm going to cover problem 15 from the homework set from Growth Models. This problem, we have a situation where we're trying to model how the hourly minimum wage has increased through time. What we're told is in 1968, the minimum wage was $1.60 an hour, and in 1976, the minimum wage was $2.30 per hour. We're also told that we should assume the minimum wage grows according to an exponential model where n represents the time in years after 1960. So one of the first things we have to think about with this problem is how this n is going to work. And n in this situation is a variable. So we know in 1960 that n is 0. That's the first year that we're beginning the model. We're told that, what that means then is in 1968, for that year, n would be 8. And for 1976, n would be 16. And the other bit of information we're given here, another bit of information, is that when n is 8, or in the 8th year that we're for our model, w is equal to $1.60. So I'm just going to write that as 1.6. Just mathematically, I don't really need to carry the extra 0 around. And when in 16 years after we start modeling, w is going to be 2.3. We're also told that the model is an exponential model. Now, in the textbook, the exponential model is written in general form like this. I think it's a t, but I don't quite remember. I'd have to go back and double check that. In this case, we're going to make that t in any case. And I'm actually going to just change p to w. And it's because traditionally for an exponential growth model, we use p's for the population. And technically the money here is the population we're modeling. But since it's a wage, I'm just going to use w. And I'm going to replace the t with n. And it doesn't really matter what letters I use. It's actually where they are positioned that matters. And it's also what the notation is. The sub-0 on the w means that's the initial wage in the model. So that would be the wage when n is equal to 0. And we're actually asked to find that in part B. And we'll do that in a little bit. And r is the growth rate. And we're going to have to find that by solving some equations. Now, in a situation like this, it's important to keep in mind that we're looking for two things here. We're looking for this initial wage, and we're looking for r. But we have 4 unknowns in this, and actually 2 of them are variables. W and n are variables. W sub 0 and r are constants, or what we call the parameters of the model. And so those are the 2 things that we're going to try to find. One of the things that you want to remember is when you're in a situation where you have an equation or a model and you need to find 2 unknowns, you need to figure out a way to get 2 equations. And we actually have a way because of the given information up here. So, for example, we know that when the wage was $1.60, I'm going to leave W0 in here. We know that that happened in the 8th year. And we also know that when the wage was 2.3, that happened in the 16th year that we're modeling. Now, the technique that we're going to use here is called substitution. That's in algebra, that's what we call this. And what I'm going to do is solve one of these equations for one of the unknowns. And so in this case, I'm going to solve for w sub 0 by dividing both sides by the 1 plus r to the 8th power factor. And what that means is that w sub 0 is equal to 1.6 divided by 1 plus r to the 8th power. And so now what we can do is, since we've isolated w sub 0 on one side, and we've got an expression on the other side that only has an r in it, if we substitute that quantity into the second equation for w sub 0, what we're going to end up with is a single equation with a single unknown. And this is a really good thing. And it actually turns out that even our ability to get this equation in this form means that we could even solve this numerically. Now I'm going to do it both ways. I'm going to solve this algebraically, but we could also solve this numerically or estimate the solution on the calculator. Now, there's a little bit of, again, it's hard. This is a pretty algebra intensive problem. And in this class, we're really not going to do a whole lot of algebra, but there is a little bit. And so basically what we have here is, I'm looking at the 1 plus r and the 1 plus r here. This is really like 1 plus r over 1. And so the 1 plus r to the 8th is in the denominator on this side of the multiplication, and 1 plus r to the 16th is in the numerator. That means that this 1 plus r to the 8th would divide out 8 of these factors in the numerator on this side. And so now the next step is to solve for r. And again, this is a lot of algebra for sure. And I know a lot of students in this class have not, either not really enjoyed algebra. Not everybody does, and is maybe even a little bit intimidated by it. But don't be too intimidated, because keep in mind that when I grade, I'm really grading as much on effort as I am on you getting the correct answer. So give it a try. All right, so now I have an equation. I have and this is a tricky one, okay, because the r is in the parentheses, is being added to the 1. There are a lot of different ways to make mistakes here. A lot of times students will take the 8 and distribute it to the 1 and write 1 to the 8th plus r to the 8th. It's not correct. Doesn't work like that. When you have the unknown in parentheses with an exponent, and again, notice on the left side, I have just a number now. It's kind of written in a complex way, but it is just a number. What we want to do here is take the 8th root of both sides of the equation, and I notate that by writing the radical symbol and then putting an 8 here. So on the left side of the equation, we have 2.3 divided by 1.6. And on the right side of the equation, I'm not going to take this. I'm actually not going to write this step, but we could write the 8th root of 1 plus r to the 8th. But what that ends up being is just 1 plus r. And the reason is because the 8th root and the idea of to the power of 8, or an exponential to the 8th power, if you take the square or the 8th root of that, the 8 to the power and the 8th root undo each other. And therefore, we just end up with 1 plus r, what's in the parentheses. And then again, the final step here would be to subtract 1 from both sides of the equation. And what we would end up with, I'm running out of room. I suppose that's poor planning on my part. See if I can squeeze it in. Minus 1 equals r. And what we want to do is estimate this on our calculators. So I'm going to get out my TI-84 calculator and show you how to do this. Now, if you happen to be using a TI-84 CE, the newest version of the calculator, and actually, it might actually be on this calculator as well. Let me peek in here. If I peek in math, I forgot about this. So yes, we have this x root of, okay, and this can represent any root. So we could do a 4th root, a 12th root, whatever root we want. Now I'm going to go back to the home screen and show you how to use this. So we type the 8 first because we want the 8th root. And then we choose x root. Yeah, I can just take a shortcut and choose the number that corresponds to it. So a little bit hard to read on my screen here. Maybe I should blow this up a little bit. And I don't know why it's doing that, but that's the 8th root. And now what I need to type in there under the radical is 2.3 divided by 1.6. And now the little arrow here is telling me hit a right arrow when you're done with the radical part. So I do my right arrow and the cursor pops out there. And then I do -1 and press enter. And what I find is that the R, or the rate of change here, is about 4.64% each year. So in other words, based on this information, the U.S. minimum wage increases by about 4.64% a year. Okay, but that's not quite, we don't quite have our model yet. So let's go to that next part. To figure out what the model is, now remember, we had two different numbers, or two different values we needed. We found R, but now we got to find W sub 0. And to find W sub 0, I can go back to one of the original equations. And so one of the original equations we had was, remember, we had 1.6 equals, now I'm going to leave the W sub 0 this time, and then replace the R with 0.0464. And remember, this was when the model was 8 years into modeling the situation. So now we have 1.6 equals W sub 0 times 1.0464 to the 8th power. And if I divide both sides by this number, because 1.0464 to the 8th power is just a number. Just a number. It's a complicated number, but it's a number. These two cancel. And we find out that W sub 0 is equal to 1.6 divided by 1.0464 to the 8th power. And this is another calculator problem. So we have 1.6 divided by the quantity 1.0464 raised to the 8th power. And in fact, I don't even think I really needed to have this in parentheses, but I don't know. I'm kind of in the habit of throwing those in there. And so what we find is that W sub 0, which is the original or the beginning minimum wage in 1960 is about $1.11. And so what that means is to write down the model now, the model is going to be, for this situation, W equals W sub 0, which we just found out was about $1.11, times 1 plus about 4.64%, and that's going to be to the nth power. Now, generally, we're going to simplify this model. I mean, this is a simple addition problem here, and so usually when, we usually wouldn't write the model in that form. Whoops. And that is the model. Now, one of the things I said I would show you is how to estimate these numbers on the using the calculator. And so, if you recall that the first equation that we needed to solve in order to find R we had 1.6 equals, actually, let me take that back. If you go back and remember, we had 2.3 divided by 1.6, and that was equal to 1 plus R to the 8th power. Now, if you were at this point and you're sitting and you were thinking, gee, I just don't know what to do here, it's perfectly okay with me, actually, in this class, especially since it's not an algebra class, to go in and use the numeric solver. So I've just pressed the math key. And what I'm going to do is go down here and go to solver and choose solver. Now, one of the tricky things about the solver is the calculator. Now, the newer calculator, the TI-84CE, allows you to enter each equation as is. But this version of the calculator, you have to have the equation in a special format where there's a 0 on one side. That's not too difficult to deal with, because notice over here, if I subtracted 2.3 over 1.6 from both sides of this equation, I would have the 0 I need on the left there. And so I'm just going to go ahead and do that. And one of the other kind of limiting things about the calculator, I guess I would say, is that when you use the solver, you have to use an X in here. So I have to replace the R and make it an X. And then I use the circumflex and the 8 for the 8th power. And now, don't worry about this part. This is, in a more advanced class, that would be an issue. But for what we're doing, that is not anything you really need to worry about. So just leave that as is. And right here, notice my cursor is right here where it says X equals. Right now it says X equals 0. That's not the solution. To get the solution, look down here where it says solve. And press alpha and the enter key. Oh, and it says go to, no sign change. All right, so then I'll go to, let's see. Oh, and what did I forget? Wait a minute. Somehow I lost my, maybe I forgot to enter it. Okay. So we need the minus 2.3 divide by 1.6. So I forgot to write that. I thought I did. And we'll try that again. Alpha, solve. Okay, so there. Notice we have the same number that I got when I did all the algebra. Now, I know this video is getting a little long, but and you can always fast forward through these parts. I mean, if you just keep in mind, and I post all these in YouTube, or not all of them, but most of them in YouTube. So you can just click forward in the video if you don't have a TI-84CE. But I want to make sure I cover how to do this for each version of the calculator. So if you have the TI-84 plus CE, then a lot of this is the same. So I press Math. I'm going to scroll down and find, I think it's got a different name. Yeah, it's called Numeric Solver here, and that's what it is. And notice how it's really nice. It gives you, it says enter E1, which is the left-hand side of the equation. I think that stands for expression 1. And then E2, which is the right-hand side. So you just enter those two things the very same way I did before on the other example. And then turns out the solution's there because we already solved it. But you would go through the same process here. Put the cursor next to the X and press second enter to solve. So it's the same idea, but the syntax on the TI-84 plus CE is a little bit different. So that would be a different way to solve for R, the R value. Now, the other equation that we had to solve in order to find the model, and again, this one is maybe a little bit easier to do, but nonetheless, the other one we had was 1.6, and I'm actually just going to even go back to this less simplified version. It's because I want to show you that, when the calculator doesn't care whether or not you've simplified this algebraically or not. And so, in a lot of ways it makes sense to not do too much algebra before you go to the solver. And I'm just going to start this one out on the TI-84CE, and then I'll switch to the other version of the calculator, but we'll alternate back and forth. So let's see, put 1.6 on the left side, and then again, remember, I'm just gonna clear this and start from scratch. So remember, this has got to be an X instead of the W0. I just use an X, and then I'm going to type parenthesis 1 plus 0. I'm just going to type it just the way I wrote it. And I'm going to use the circumflex here for exponent. That's to the 8th power. And notice this is the same x from before. So the calculator doesn't actually solve for x until we do the alpha enter part. And notice there, that's the same number we got before. And then I'll just quickly switch back to the TI-84 plus to go through this. So I'm still in the solver. You get to the solver the same way, Math, and go to solver. And I can go up here and just modify this equation. And so, and keep in mind, I got to subtract the 1.6 from both sides. I forgot to do that last time, but let's see if I remember this time. I don't really need the 0 in front of the decimal, but I need the next one. Close that parenthesis, raise that to the 8th power, subtract 1.6, and then a down arrow, and then alpha, enter, and there's the x value. So I think that's pretty cool because really, I mean, a lot of mistakes are made in the algebra steps. And the other thing is, this is a really great way to check your work. And, again, in this class, there's not a lot of algebra. And I really am not focused on whether or not you're doing every single step of all of this correctly. I'm really trying to see that you're getting the bigger ideas. But we're going to do some of the detailed problems too in the homework and stuff like that along the way. Okay, now getting back to the original problem here, finishing this up. Okay, so let's see the model. Let me write that down. So the model was W equals about $1.11 in the first year, 1.0464 to the nth power. And there were a couple other questions there that we were asked to address. And actually, I'm going to go back and double check this. I kind of forgot what they were. Okay, so find an explicit formula. So maybe I'll do it on this page. I'll come back here and just answer each question, just to be very clear. So that is the explicit formula, or what we might call, what I like to call the model. What does the model predict when the minimum wage in 1960? Well, what we have to remember is that in 1960, n is 0. That's where we're starting the model. So this is actually what the problem is asking us to find, is W0, which is going to equal 1.11 times 1.0464 to the 0 power, and any number, not any number, any number greater than 0 to the 0 power is 1. That means this must be 1.11, like we would expect it to be. Actually, I should be really clear. Any number except 0. 0 to the 0 power is not 1, but any real number other than 0 to the 0 power is 1. I haven't taught algebra in a long time, I'll be honest. I have to make sure I say these things correctly. All right, so in any case, for part C, what we're asked to do in part C is check our model. In a way, this is like something, really important to keep in mind. It's important to, as you're using this kind of a model to make predictions, as you move into the future with the model, it's a really good idea, or it's really important to check the model with the data, the true data. So in other words, what does the model predict? Well, the model predicts that the minimum wage in 1996 should be, I got to think about what this exponent is going to be. How many years from 1960 is 1996? I think that's 36 years. So that exponent would become 36. And what does that equal to? Well, I'm going to get my calculator out for that. So let's see. I'm going to go so I can quit back to the home screen. I'm just going to clear that. All right. 1.11 times 1.0464 raised to the 36th power. So our model would predict about $5.68. So the wage in 36 years, what was that? I already forgot. $5.68. So our model is overestimating here. The actual wage is $5.16 or 15 cents. So we'd want to tune our model. If we were mathematical modelers, that would be our next step. We would take that data point into account and lower the rate, because what this means is the true growth rate, exponential growth rate here is not, well, actually, there are a couple of things it could mean. The first thing it could mean is that exponential growth rate is actually less than 4.46%. But it could also mean we're using a different model. It's interesting to me that when we look at this point, and again, I'm going to kind of verge off into, and I'm done with the problem, so this is a little bit of an extra kind of discussion item here. So let's see, we got 8, we've got 16, and then we got a data point. Let's see, I better keep the scale correct here. So we'd go 8, we go 16, we'd go 24, I'm counting by 8s, and then 8 more would be 32, 8 more would be 40, and that would be the N axis. And then up here is the W axis, and let's see, we're going from a little more than $1 and I'm using like a tablet to try to draw this, so oh well. Okay, so we know at year 8 we know that the wage was about $1.11, so I would put a point about there. We know at year 16, no, that's at year 0. Sorry, let me get this correct here. So that's at year 0 is about $1.11. So I need to take that one out of I made a mistake there, darn it. We know that at year 8, the wage was about $1.16. Well, it's not much above that, but a little bit above it. Year 16, we're up at $2.30. And at year 36, which, let's see, 36 I think is 4 plus 32. I think that's about 36 there. Our model predicts that the wage will be up here at $5.68, which is about right here. And you can see that if I try to connect all these dots with sort of like a smooth curve, and I'm doing an okay job, I guess, you can see that that's the exponential, what the exponential model would look like. Something like that. But in reality, what we found is that the wage was $5.15. So that would be just a little bit more than 5. So this point's actually down here a little bit. So we might ask, well, of course, at some point, the growth would just be a linear growth, maybe. So in any case, we'd probably still use an exponential model, though, and just adjust it. So the idea would be we'd have the same kind of shape curve here. It's just that it turns out that wage wasn't growing quite as fast. Okay, so that's it for this video. I hope that helps, and I'll see you next time.